In the next subsection, I want to discuss the first method that is used as given in practical application, and that's the Lempel-Ziv Welch compression algorithm. I want to first motivate this with a little warm-up exercise. It's a little wordplay, not necessarily to be taken too serious. It definitely is about, so peas porridge, I had to look this up when I moved here. This is some British local cuisine, not scouse though, but it exists, and it's some type of stew or soup. Doesn't matter too much. So the core idea of Lempel-Ziv Welch is to represent parts of the text using parts of the text that you've already encoded. And this is very nicely illustrated in this example, and I want to also shoot up the question for this. I'd like you to give me the content of this second to last row, so this one. I won't really explain how this works. I think it's the graphical explanation is self-explanatory. And it shows that for some texts, like this poem, which is fairly repetitive, as you will see if you decode it, you only really store the printed letters, and the other boxes are just a number or a pointer back to the coded text. So these take a certain fixed small amount of space. So it might already be obvious that this is a method that can, again, drastically reduce space. And it works fairly well for a variety of data, in particular also for natural language text. Yeah, I see one good answer already. Maybe I'll just leave it open for a sec, but then you don't see this picture anymore. I probably have to just be a little patient here. Okay. Maybe at least 2 more people can send in their answer. The ones I got so far are fine. Mostly. So maybe I should add a word of explanation how this should work. If there's a box that's empty, then there is an arrow attached to it, and you should follow that, and that will point to somewhere where you can copy what goes in this box. So this fourth line says 9 days old because you copy this substring from cold. Now sometimes you copy something that's actually not there itself, but is copied from somewhere else. So here you have this this peas porridge. Well, that itself again is not fully here because you have certain things that are copied from other places, like here again. So you have to follow all these pointers. But if you do it, then it'll read like peas porridge hot, peas porridge cold, peas porridge in the pot, 9 days old. Some like it hot, some like it cold, some like it in the pot, 9 days old. I'm not recommending eating nine days old peas porridge, but that's what it says. So yeah, many of you got this. Good. Let's see how this connects to a more serious discussion of Lempel-Ziv. But the idea is exactly that. Use references to previously occurring things. But let's start from scratch and properly. Huffman coding and run length encoding both talk about single characters, either by their frequency overall in the text or by being the very same thing repeated, but we don't have that so often in many inputs instances. What we more often find is that substrings, certain phrases or words, are more frequent than others. For English texts, these are the most frequent ones, and I'm sure you would have found others in other languages. stuff like in HTML, you often see these things as combinations, and there's many, many others. And I guess you can imagine how this goes. Now you could think you could try to put some application-specific encoding together where you give a special character for these phrases that you think occur often, or maybe you could try to find out which phrases are more frequent than others. Yeah, let's stop the poem now. You can check the recording and go through this again if you want in detail. So you don't want to hard code this, or you don't want to have to specify or divide phrases into this is frequent, this is not frequent. We want a method that organically finds these by itself. And Lempel-Ziv does exactly that. It's a family of compression algorithms, not a simple thing. The idea is what you've seen in this poem. You have a certain part of the source text, and instead of encoding it literally by giving all the characters, you say, I've seen this before. It occurred at position 5 and the following characters. So you store things by a reference, and I will be very precise and concrete when we discuss the actual Lempel Ziv Welch. So a code word here is no longer encoding a fixed thing in every instance, but it encodes a single character or a substring of something we've seen before. And depending on the source text, that can be a different string each time. The important part will be that both the encoder and the decoder must have seen that substring before. Otherwise, you could not decode it again. But this will work out. There are many variants of Lempel-Ziv. They differ in the details of what is allowed. The original version would allow copying something from itself. Not sure if that makes a lot of sense. It's also, can you only copy things that were a phrase before, or can you start at any point? That's the differences, but we won't discuss that here. We'll focus on one representative variant of Lempel-Ziv, which also is the cleanest and the most widely used in practice. And that is the Lempel-Ziv Welch algorithm. So historically, Lempel and Ziv came up with the core idea in a sequence of papers, and then Welch later rephrased it a little bit and added more twists to that, just make the method a little rounder for implementation. But the historic context aside, we'll just look at the final result from this history. I won't go into the details, but I just want to today I just want to give the core setup. Lempel-Ziv Welch will be an instance of a variable to fixed coding. So we will fix a length for the code word. A typical choice in practice is 12 bits. And then all the code words will use exactly k bits, but they will represent a variable portion of the source text. And this is the opposite of what we used in Huffman. There we had a fixed to variable encoding. Fixed was one character is encoded at a time. Variable was the length of the code word. Here we flip this around. We do it just the opposite way. We represent something of various length, and the method will have to tell you how this works. And it's represented by a fixed length code.